Welcome! In this session, we'll be exploring a fun and interesting problem called Kids with the Greatest Number of Candies. We'll break down the problem, discuss different approaches, and understand the best way to solve it efficiently. Let's dive in. The problem is about determining which children can have the greatest number of candies if given a specific number of extra candies. You're given an array called Candies, where each element represents how many candies a child currently has. Additionally, there's an integer extra candies that specifies how many additional candies you can give to one child at a time. The goal is to return a Boolean array where each element corresponds to whether a child can have the greatest number of candies among all children if they receive all the extra candies. If a child would have the greatest number of candies after getting the extra candies, the value is true. Otherwise, it's false. Let's look at some examples to make this clearer. In the first example, the candies array is 2, 3, 5, 1, 3, and extra candies is 3. To calculate the result, we check each child one by one. For the 0th child, giving them 3 extra candies results in 2 plus 3 equals 5 candies, which is the greatest number among all children. So the result for the 0th child is true. For the first child, adding 3 extra candies gives 3 plus 3 equals 6, which is also the greatest, so the result is again true. Similarly, the second child ends up with 5 plus 3 equals 8, the greatest number, so the result is true. However, the third child with 1 plus 3 equals 4 does not have the greatest number of candies, so the result is false. Finally, the fourth child gets 3 plus 3 equals 6, which is the greatest, so the result is true. The final output is true, 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 false, true. Now, consider the second example. Here, the candies array is 4, 2, 1, 1, 2, and extra candies is 1. For the 0th child, adding 1 extra candy results in 4 plus 1 equals 5, which is the highest number of candies, so the result is true. For the first child, adding 1 extra candy gives 2 plus 1 equals 3, which is not the greatest, so the result is false. Similarly, the second, third, and fourth children also do not achieve the greatest number of candies after receiving the extra candy. Therefore, the result for these children is false. The final output for this example is true, false, 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 false. Moving to the third example, the candies array is 12, 1, 12, and extra candies is 10. For the 0th child, giving them 10 extra candies results in 12 plus 10 equals 22, the highest number of candies, so the result is true. For the first child in the third example, adding 10 extra candies results in 1 plus 10 equals 11, which is not the greatest, so the result is false. Lastly, for the second child, adding 10 extra candies gives 12 plus 10 equals 22, which is the greatest number of candies, so the result is true. The output for this example is true, false, true. Now, let's discuss the constraints and edge cases. The constraints specify that the number of children will be between 2 and 100, and each child can have between 1 and 100 candies. The extra candies value ranges from 1 to 50. For edge cases, if all children have the same number of candies, giving any child the extra candies will always result in true. If extra candies is very small, only the children with the most candies will likely end up with true. Conversely, if extra candies is large, all children may have the greatest number of candies, resulting in all true values. The problem size is small enough that no advanced optimizations are needed for performance. To begin solving this problem, we can consider a brute force approach. Here, the idea is to iterate through the candies array multiple times. For each child, we calculate the number of candies they would have if given all the extra candies. Then, we compare this total with the maximum candies that any child currently has. If the total meets or exceeds this maximum, that child could potentially have the greatest number of candies. However, this approach is inefficient because it involves repeatedly finding the maximum value in the array for each child, which has a complexity of O(n) per iteration. With n children, this results in a total time complexity of O(n) squared. Such an approach becomes impractical for larger inputs, for example, when n exceeds 10,000. This repeated and redundant work makes the brute force method computationally expensive and unsuitable for scalable solutions. A more efficient approach involves pre-computation to minimize redundant work. The first step is to calculate the maximum number of candies among all children in a single pass, which takes n time. Once we have this maximum value, we can iterate through the array again, checking for each child whether their current candies plus extra candies equals or exceeds this maximum. If the condition is true, we add true to our result list, otherwise, we add false. This approach separates the maximum finding step from the condition checking step, ensuring that we only perform a single pass for each task. The overall time complexity of this method is n, because both steps, the pre-computation of the maximum and the iteration to check conditions, are linear in time. This makes the approach highly efficient and well-suited for larger inputs. By eliminating unnecessary calculations, this method not only improves performance but also simplifies the algorithm. Another possible solution involves sorting the array to determine the maximum number of candies. After sorting, the maximum value would be the last element in the array. We would then iterate through the array, checking whether candies I plus extra candies meets or exceeds this maximum value. However, this approach has a higher complexity due to the sorting step, which requires n log n time. The subsequent iteration to check conditions adds n, resulting in a total complexity of n log n. While sorting provides a way to find the maximum, it introduces unnecessary overhead because the maximum can be determined much more efficiently in n using a single pass. For this problem, where only the maximum value is needed, sorting is overkill and not the optimal choice. The optimized approach is the most effective strategy for solving this problem. The key insight is that determining whether a child can have the greatest number of candies depends solely on candies I plus extra candies compared to the pre-computed max candies. By calculating the maximum value in one pass and reusing it, we eliminate redundant operations and achieve a solution that is both elegant and efficient. The realization that sorting or repeatedly finding the maximum is unnecessary simplifies the algorithm while maintaining its correctness. This approach achieves linear time complexity, making it scalable for all input sizes. While the brute force and sorting-based methods may be easier to conceptualize initially, their higher time complexities make them less practical. The chosen strategy strikes the perfect balance between clarity and performance, offering a solution that is both intuitive and highly efficient. In this problem, we have an array called Candies, where each element represents how many candies a particular child has. We're also given an integer extra candies, which represents the additional candies we can give to any child. The goal is to determine, for each child, if giving them all the extra candies would result in them having the greatest or at least an equal number of candies compared to all other children. The result will be a Boolean array, where each entry is true or false depending on whether the child meets this condition. To approach this, we first need to compute the maximum number of candies that any child currently has. Then, for each child, we calculate their new candy count if they were given all the extra candies. We compare this value to the current maximum. If it's greater than or equal to the maximum, we mark the child as true in the result. Otherwise, we mark it as false. To implement this, we can break it down into several steps. First, we compute the maximum value in the candies array using the max function. This gives us the current maximum number of candies, which we'll use as a reference point for comparisons. Next, we initialize an empty list called result to store the Boolean values for each child. Then, we iterate through the candies array. For each child, we calculate their potential candy count by adding extra candies to their current count. We check whether this new value is greater than or equal to the maximum value we computed earlier. If it is, we append true to the result array, otherwise, we append false. Once we've processed all the children, we return the result array as the final output. This approach ensures that each child is evaluated in just one pass through the array, making it efficient. There are a few edge cases to consider in this problem. For instance, if all the children start with the same number of candies, giving extra candies to any child will always make them have the greatest number of candies. Another scenario is when extra candies is very small, such as 1. In this case, children who have significantly fewer candies than the current maximum might not be able to reach or exceed the maximum, even with the extra candies. To solve the problem efficiently, we rely on key insights. First, by pre-computing the maximum value in the array, we eliminate the need for redundant comparisons during the iteration. This keeps the time complexity to O(n), as we only need one pass to find the maximum and another pass to construct the result array. The space complexity is O(n) as well, due to the storage required for the result array. We also use simple data structures, the input array to store the initial candy counts, the output array to store the results, and a temporary variable to store the maximum candy count, all of which are accessed in constant time. Let's walk through an example to see how the algorithm works step by step. Suppose the input is candies equals 2, 3, 5, 1, 3, and extra candies equals 3. First, we calculate the maximum number of candies in the array, which is 5. Next, we initialize an empty list result. Now, we iterate through each child. For the first child with 2 candies, adding 3 results in 5, which is equal to the maximum, so we append true. For the second child with 3 candies, adding 3 gives 6, which is greater than the maximum, so we append true. The third child already has 5 candies, and adding 3 gives 8, which is also greater than the maximum, so we append true. The fourth child with 1 candy gets a total of 4 after adding 3, which is less than the maximum, so we append false. Finally, the fifth child with 3 candies reaches 6 after adding 3, which is greater than or equal to the maximum, so we append true. The final result is true, 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 false, true. The time complexity is O(n) for finding the maximum and iterating through the array, and the space complexity is O(n) for storing the result. If memory is constrained, we could compute the maximum on the fly during iteration, but the current approach is already efficient for most scenarios. This solution to the problem kids with the greatest number of candies is implemented in Python. The goal is to determine, for each child, whether adding the specified number of extra candies to their current count would make their total count the greatest or equal to the greatest among all children. We start by calculating the maximum number of candies that any child currently has using Python's max function. This step gives us a reference point to compare with. Next, we initialize an empty list called result to store the Boolean values for each child. The list will eventually indicate whether each child can have the greatest number of candies after receiving the extra candies. We then iterate through the candies list using a for loop. For each child's candy count, we calculate the new total by adding extra candies. We check if this new total is greater than or equal to max_candies. If it is, we append true to the result list, otherwise, we append false. Finally, after processing all children, we return the result list. This solution runs efficiently in O(n) time, where n is the number of children, since we compute the maximum once and perform a single pass through the list to evaluate each child's condition. The space complexity is O(n) due to the result list that we create. This implementation is concise, accurate, and handles all edge cases, such as when there is only one child or when all children have the same number of candies to start with. This is the Java implementation of the LeetCode problem number 1431, kids with the greatest number of candies. The solution mirrors the Python logic, where we first determine the maximum number of candies a child currently has. Then, for each child, we check if adding the extra candies would make their total equal to or exceed the maximum. The method utilizes Java-specific features such as the ArrayList for storing results, and type declarations are required for variables. The implementation ensures logical equivalence to the Python solution while adhering to Java syntax and conventions. Here, we start with a simple example where the candies array is 2, 3, 5, 1, 3, and the extra candies value is 3. The first step is to find the maximum number of candies any child currently has. Using the max function on the candies array, we find that the maximum value is 5. Next, we initialize an empty list called result, which will store Boolean values indicating whether each child can have the greatest number of candies after receiving the extra candies. Now, we begin iterating through each child's candy count. For the first child, who has 2 candies, we check if 2 plus 3 is greater than or equal to 5. Since 5 is equal to 5, we append true to the result list. For the second child, who has 3 candies, the condition 3 plus 3 equals 5 evaluates to true, so we append another true. At this point, the result list is true, true. Now, we continue iterating through the candies array. For the third child, who has 5 candies, we check if 5 plus 3 is greater than or equal to 5. Since 8 is greater than 5, we append true to the result list. For the fourth child, who has 1 candy, we check if 1 plus 3 is greater than or equal to 5. Since 4 is less than 5, we append false to the result list. Finally, for the fifth child, who has 3 candies, the condition 3 plus 3 equals 5 evaluates to true, so we append another true. The final result list is true, 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 false, true, which we then return. This means the first, second, third, and fifth children can have the greatest number of candies, while the fourth child cannot. In this example, all children start with the same number of candies. The candies array is 4, 4, 4, 4, and the extra candies value is 2. The first step is to find the maximum number of candies. Since all values are equal, the maximum is 4. Next, we initialize an empty result list to store the Boolean outcomes. As we iterate through the array, we check for each child if their candies plus the extra candies meet or exceed the maximum. For the first child, the condition 4 plus 2 equals 4 evaluates to true, so we append true to the result list. The same condition holds true for the second, third, and fourth children, so we append true for each of them as well. The final result list becomes true, 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 indicating that all children can have the greatest number of candies. We return this list as the output. In this edge case, we have only one child, with a candies array of 7 and an extra candies value of 5. Since there is only one child, the maximum number of candies is simply the value 7. After finding the maximum, we initialize an empty result list. Next, we check if this child's candies plus the extra candies meet or exceed the maximum. For the single child, the condition 7 plus 5 equals 7 evaluates to true, so we append true to the result list. At this point, the result list is true. The final result for this case is true, which means the only child can have the greatest number of candies after receiving the extra candies. Overall, the solution works by first identifying the maximum number of candies any child currently has. Then, for each child, it evaluates whether the candies they have, plus the extra candies, are greater than or equal to this maximum. The results are stored as Boolean values in a list. This algorithm is efficient, with a time complexity of n, where n is the number of children, as we only loop through the candies array once and perform constant time operations for each child. To determine the time complexity of this solution, we break it into two main operations. First, we need to find the maximum number of candies in the given array. This is achieved using the max function, which iterates through the entire list once. If there are n children, or in other words, the size of the candies array is n, this operation takes n time since each element is visited exactly once. Next, we iterate through the candies list again using a for loop. For each child, we evaluate whether their candies, when combined with extra candies, are greater than or equal to the maximum value. This comparison is done in constant time, 1, for each child. Given that there are n children, this loop runs n iterations, resulting in an additional time complexity of n. When we sum these two steps, n, for finding the maximum value and n, for the loop, the total time complexity of the solution becomes n. In terms of space complexity, we analyze the memory requirements of the solution. First, the input list candies takes up n space, where n is the number of children. This is because the input array must be stored in memory to perform the operations. Next, we consider the space needed for the output. The result array, which stores a Boolean value for each child, also requires n space since it contains one element per child. Beyond the input and output storage, we account for auxiliary storage. Here, the variable max_candies holds a single integer value, using 1 space. Likewise, the loop variables and any intermediate computations also occupy only a constant amount of memory, 1. Adding these together, the dominant factor is the space used for the input and output arrays, making the overall space complexity n. When comparing this optimized approach to a naive solution, we can see a significant difference in efficiency. A brute force method would involve comparing each child's candies, after adding extra candies, against all other children's candies. This requires iterating through the candies array for each child, leading to a time complexity of O(n squared). However, by optimizing the solution, we avoid this nested iteration. Instead, we first determine the maximum value in the Candies array, and then evaluate each child's condition in constant time during the loop. This reduces the time complexity from O(n squared down to O(n). Furthermore, the time complexity remains consistent across all scenarios: best, average, and worst case. Regardless of the input, the max function and the loop both traverse the array once, ensuring the time complexity is always O(n). To confirm the time and space complexity, we can break the operations down step by step. The max function iterates through the array once, taking linear time, O(n). The loop then performs a constant time comparison for each child, resulting in n*(O1), which simplifies to O(n). Adding these two components, the total time complexity becomes O(n) plus O(n) equals O(n). For space complexity, the output array, which stores one Boolean value per child, is proportional to the size of the input, requiring O(n) space. Since the other storage requirements, such as the max_Candies variable and loop variables, are constant, they do not affect the overall space usage. Therefore, the algorithm achieves linear time complexity, O(n), and linear space complexity, O(n), with no additional overhead. When tackling this problem, there are a few common mistakes to watch out for. First, failing to consider edge cases can lead to incorrect results. For instance, if extra Candies is 0 or all values in the Candies array are equal, the logic might break down. Testing edge cases, like the smallest and largest possible inputs, ensures robustness. Another frequent issue is incorrect comparisons. Some may forget to pre-compute the maximum value in the array, or they might recalculate it unnecessarily inside a loop, which can increase runtime or introduce errors. Overcomplicating the solution is another pitfall. Using nested loops to compare all elements results in inefficient O(n squared) complexity when a pre-computed maximum allows for a simpler O(n) approach. Finally, modifying the input array, like directly adding extra Candies to elements, can corrupt the original data, which might still be needed later. Always aim to preserve input integrity. Misunderstanding the problem statement is another common issue. Some interpret greatest number of Candies as requiring a strict comparison, where Candies, I, plus extra Candies must be greater than the maximum value, instead of allowing equality. Always ensure you thoroughly understand the requirements, especially in interviews. Speaking of interviews, this problem emphasizes the importance of recognizing patterns. It's essentially a variation of find the max and compare, a common problem type. Identifying this pattern can help simplify your approach. For instance, the optimal solution involves one pass to find the maximum value in O(n), and another to evaluate conditions for each child, maintaining an overall O(n) complexity. During interviews, it's essential to highlight such efficiencies and explain your thought process clearly. Emphasize edge case handling, logical clarity, and efficiency, as structured problem solving is highly valued by interviewers. This problem is part of a broader category of challenges that involve finding and comparing maximum values in arrays. For example, the problem itself, kids with the greatest number of Candies, directly applies this concept. Another related problem is to-sum, which involves efficient iteration and meeting specific conditions, often under time constraints. Remove element is another example, focusing on array manipulation with minimal extra space, which is a useful skill in scenarios requiring in-place modifications. Finally, replace elements with greatest element on right side also revolves around identifying maximum values, but with a twist: it requires working from the right side of the array instead of the left. Practicing these problems will deepen your understanding of array manipulation and comparisons, helping you build a strong foundation for similar challenges. There are multiple approaches to solving this problem, each with its own trade-offs. The two-pass approach is straightforward. It involves one pass to determine the maximum value in the Candies array, followed by a second pass to check the condition for each child. While simple and efficient with an O(n) time complexity, it does require 2 iterations. Alternatively, the single-pass approach combines both tasks into one loop. While this saves an iteration, it requires more careful logic to ensure conditions aren't missed, making it slightly more error-prone for beginners. Lastly, there's the brute force approach, where you compare each child's Candies with all others after adding extra Candies. Although conceptually simple and a good starting point for understanding the problem, this method is highly inefficient with an n² complexity. It's best used as a stepping stone before refining your solution to one of the more optimal approaches. Great job! We've covered the problem kids with the greatest number of candies, reviewed approaches, and emphasized the importance of optimization. Keep practicing and challenging yourself with similar problems. Thanks for watching, and don't forget to like and subscribe for more content. See you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!